Okay, in today's lesson, number 2 in Chapter 8, we're going to cover bond energies 8.8, Lewis structures 8.10, exceptions to the octet rule 8.11, and resonance 8.12. So each type of bond has a certain amount of energy associated with it. And you know that when we break bonds, we have to absorb energy, and when we make bonds, we release energy. In my book, this is on page 374. It's probably going to be around the same place, but maybe not exactly the same page in your book. And in order to do problems where you have to calculate the overall energy involved in a reaction, you need to use this table. One thing that I do want to draw your attention to is that in carbon dioxide, the CO double bond has a special energy value, which is 799, which differs from the regular CO bond energy of 745. So please pay attention to that if you're dealing with CO2 in a molecule. All right, let's do some practice problems with this. So we need to calculate delta H for the reaction that you see here. Now, one thing that you have to remember is there's been different places where we've calculated delta H before. We've calculated delta H when we used the heat of formation table, which is when we form 1 mole of a substance. And recall that that is always the sum of the products minus the sum of the reactants. And in another example with Hess's law, we had to manipulate reactions, either double them, reverse them, halve them, in order to come out with the final reaction, because a reaction happens in a series of steps. And in that case, we were summing the delta H's of the subsequent reactions. So finally, in bond energies, which is what this section is all about, we're going to do bonds broken minus bonds formed. So I just want to review that. So this is going to be the sum of bonds broken minus the sum of bonds formed. And I know I said that in the previous lesson, but we didn't get to do any sample problems. I find the easiest way when you're starting out to do these problems is to actually draw them. So what I do is I want to make sure I don't miss any bonds. So when I look at CH4, I know that it's C with 4 H's around it. Plus, I have 2 Cl2s. So I've got Cl, Cl, and Cl, Cl. I also have 2 F2s. So FF, FF. And I'm not telling you that you have to do this. I'm just using it as a learning point so that you can see what's happening. And then we have CF2, Cl2. It doesn't really matter which side goes where, because we are using one dimension to draw a three-dimensional object. We have 2 HFs, and 2 HCl's. And I'll show you why I did that. Okay, that's because my arrow didn't want to get put in here. So now we have to look at the bond energies that are associated with these. And the reason why I drew them out is because I want to make sure that you don't short any of the bonds. So remember, we're starting with bonds broken. Right? So this is your bonds broken side minus bonds formed. All right, so let's start over here. We have CH4, and in that we have 4 CH bonds. So what I'm going to do is I'm going to go up to my chart. I'm just going to do this once. I'm going to find CH. I see that CH is 413. Okay, so I'm going to come back down here, and I've got 4 times 413 because there's 4 CH bonds. Plus, I have 2 Cl-Cl bonds, and Cl is 239. And I have 2 FF bonds, and F is 154. And that's going to be minus my bonds formed. Over here I have CF2, Cl2. So within that molecule I have 2 CF bonds, and I have 2 Cl bonds, which is 339, plus I have 2 HF bonds, which is 565, plus I have 2 HCl bonds, 427. So I have a total here of 2438 minus my total here of 3632. So I get a grand total of 1,194 kilojoules. Negative. Make sure I got that negative sign in there. So what that tells us when we're looking at the reaction is that although bonds have been broken and new bonds formed, the overall reaction is exothermic. All right, let's look at another one. So this one's a little more challenging in the sense that the drawing of the molecules is complicated, and you wouldn't get one like this on the exam. And we haven't talked about drawing Lewis structures yet, so don't worry about that. So what you have is 5N2O4. So how we would draw N2O4 is like this. We would have N, N, and we have 5 of these, okay? So we've got 2 double bonds and we have 2 single bonds. So the O's with the single bonds have 6 valence electrons. The O with the double bonds have the 4 electrons around it. Plus, we have N2H3CH3. So we've got N2, so we've got 2 N's bonded to one another, and that's bonded to a C that has 3 H's around it. And then we have 3 hydrogens around the ends. So we have 2 coming off the N, 1 here, and a lone pair. Like I said, I'm doing this for the practical sense of showing you how to do these problems. And we have 4 of those. And that's going to yield 12 waters. Everyone should remember how to draw water. Plus 9 nitrogens. Well, that's going to be a triple bond. Plus 4 CO2. All right, so let's break this down as far as values. I'm going to list, because this one's really complicated, underneath what I have. If you don't want to do this part, that's fine. You can wait till I get right to the numbers. So when I look at this first molecule, I see that I've got 2 N-double-O bonds, right? I also see that I've got an N-N bond, and I also see that I've got 2 NO bonds. So that's basically what I'm going to write down here. I have 5 times 2, and I have N-double-O bonds. I also have 5 times 2 NO bonds. And I have 5 NN bonds. Next I have 3 NH bonds. I also have 3 CH bonds. I also have an NN bond, and I have an NC bond. Okay, so let's write that all down below. 4 times 3 NH bonds. I have 4 times 3 CH bonds. I have 4 times 1 of an NN bond and 4 times 1 of an NC bond. Then I go to my water, okay, and I have 12 times 2 HO bonds plus 9 N triple bonds plus 4 times 2 C double O bonds. Okay, let's do the math on this. Okay, so we have, starting from the bottom up, we have 5 times 160, that's the NN bond, plus we have 10 times 201, which is the NO single bond, plus we have 10 times 607, which is the N double O bond. In the next molecule, we have 4 NC bonds at 305 plus 4 NN bonds at 160 plus 12 CH bonds at 413 and 12 NH bonds at 391. Okay. Then we have to subtract the bonds broken. So I'm going to do that right over here. We have 12 times 2, which is 24, HO bonds at 467, plus we have 9 triple N bonds at 941, plus we have 4 times 2, we have 8 C-double-O bonds, and that's specifically in the carbon dioxide, which is going to be 799. So when we do the math on all of this, I get $880 for this first set of brackets, 8,880 for this set of brackets. And then over here, for the second set of brackets, I get 11,508. So when I add the two of them together, I get $20,308, and then our bonds formed came out to 26,069. So bonds broken minus bonds formed came up with a grand total of negative 5,681 kilojoules. Now, you will never see a problem like this, I promise you. More realistically, you'll see one like in example 1. Just wanted to show you how you really go about paying close attention to the types of bonds you have, the number of bonds you have, double checking your math, so on and so forth. Now, this bottom example, example 3, I'm going to talk about this one in class on Monday. This is also a little bit of a bear of a problem, and you might have to do part of it, but certainly not the whole thing. So this is going to end this lesson, and you need to watch the next lesson as well, which is going to be on Lewis structures, formal charge, and resonance. And then you'll be able to do the problem set.